Assalamualaikum. I'm going to perform a short video tutorial on how to run the Newton Raster test bench and explain things inside of the test bench outputs. Okay, let's make the project. We'll save the directory. We'll add the files. We'll add the three files on the they are top level, stage, and pipeline. The rest of the VHDL files are similar implementation of non-restoring, but they have errors in their implementation. Okay, the exact files and they are in VHDL. Okay, let's use this code for now. None. Model 7 Terra, VHDL, uncheck. Next, finish. Okay, now it has loaded up. We'll open the files. We'll set top level as our top level entity. Now, if you remember, we'll perform some settings. We'll make sure this is the right one. Okay, now we'll go into settings. We'll make sure this is VHDL 2008. Next, we'll go to simulation. And now click apply. Now go ahead and we'll add a new file. File, new, a VHDL file. Now copy the contents I gave you. We'll copy it here. We'll copy the name of the entity because when we're going to save it, we'll use this particular name, top level underscore tb. Should match the name of the entity. Now this file has been added. Now we have to specify that this file is not part of the design source, but this is part of the test bench. We'll go to assignments, settings, simulation, compile test bench. We'll add the test bench, new, test bench name, top level tb, and the simulation. And we should generally end it before it becomes too long. So we know that it takes around 10-15 clock cycles, and each clock cycle is 10 nanoseconds, so it should run for about 150, but to be on the safe side we'll add 170 nanoseconds. What is the file name? Top level tb. Okay, okay, apply. Make sure everything else is alright. Make sure this is VHDL 2008, and also make sure that this file has been added. Okay, now we have specified that these three files are not part of the design source, and this is one is part of the test bench. Okay, now we're going to go ahead and run the RTL simulation. The analysis and elaboration has completed. This particular thing tells us that if there were any errors or syntax errors, or there any logical errors in not necessarily logical errors, but any syntax errors or any abnormalities in our code. If this is green, that means there are no abnormalities in our code or in our test bench. Now the test bench has itself loaded up. Now the test bench has loaded up and it has ran for 170 nanoseconds. We will scroll up and zoom out. Okay, so as you can see, these are our clock cycles, and this is our reset. Till there is reset, there is nothing on the output. Okay, uh, for as you can see, uh, there are six outputs. There are only three inputs. So as per non-restoring algorithm, it produces two outputs, the quotient and the remainder. This is quotient and this is the remainder. So it takes three inputs, three different values for which will produce the quotient and remainder of. We'll convert them into now, unsigned decimal for our ease of understanding. Okay, so I have converted all the radix for each of the inputs and outputs to unsigned decimals. Okay, we enter the value at 10 nanosecond in the just after the first clock cycle when the reset goes to 0. The values that are entered are 100 if we find the quotient and remainder for 100, for 20,000 and 65,121. Why 65,121? This was back when we were testing this test bench. We wanted to test uh, the maximum number of input that we could give. Okay, because the input is, I guess, 16-bit. Okay, as you can see, the outputs change from if we look at the quotient for S1, which is the corresponding quotient for X1. S1 we get 1, 5, and then 7. So why is there an iteration? Because it is going through its stages to find to find its answer. Once it has found its answer, only then uh, it will stop. So it stops at 7. So that means it has found its answer. Now to calculate, we'll just open up our calculator and use the formula given in your project report, that is s square plus r. We'll go back where were we. This is this is s, so s square, and the corresponding remainder is 51. So this should total to 100, and it does. So for 20,000, what we're going to do now is take the square for S2, which is 127, the final value, and add that with its corresponding remainder, which is R2 3871, and we should get the value for our input, which is 20,000, and we get 20,000. So, and now for the final one, 65121, uh, we have the quotient for that S3, which corresponds to the input X3, which is 255. We'll take a square, and the remainder for that one is 96, which gives us exactly 65121, which corresponds exactly. Now as you can see, the maximum number of iterations it took was here. Now we're going to calculate how many clock cycles it takes. One clock cycle, two clock cycle, three clock cycle, four clock cycle, 5, 6, 7, 8, 8.5. So it took 85 nanoseconds to calculate our answer, the quotient and the remainder for the maximum number of values. If the value was smaller, if the value was small, just like for our x1, which is 100, we got the value in how many clock cycles? 1, 2, 3, 4, 4.5. So that means the lowest amount, we got was 4.5, and the maximum we got was 8.5. That means uh, we should always look at the maximum number of clock cycles it takes. If you remember Newton Raphson, it took us 12 clock cycles because there were 12 stages. Now here it takes us the maximum of 8.5 clock cycles, which means this is faster. So if your program is faster, it is more. Uh, this is the one that you should use. So if your professor asks which one is faster, non-restoring, but as you know, it outputs in this way and not exactly in the square root form that we are used to of. So this is currently working in, as if you remember, the long division method. So this concludes. Also, let's take a look at the this bench as well. Okay, so this is the these are our library declarations. This is our entity declaration. Now this is the architecture. Here we are going to describe the component that we are going to instantiate. The component that we are instantiating is top level. We will take all the inputs and the outputs which are inside of the top level file, which is clock, reset, x1, x2, x3, s1, s2, s3, r1, r2, r3. These two are outputs and are unsigned, 7 8 bits and 16 bits, and input is 15 bits, and these two are single bits, the clock and reset. We have matched it exactly as is because we are instantiating. So we are calling this main file, the top level file, the top level entity. Now we are going to declare our on signals. These are our on signals that we are going to use. So these should match exactly uh, as the thing we are instantiating, the top level. Okay, so these should match. These were given by your professor. These are the ones that we made. The clock reset and all of these, you can name them exactly the same. Now we are basically this is called port mapping. So what we are doing is, this is our clock, we are mapping this to your professor clock. Okay, so this one means this one means this. We're just connecting each and every signal of our test bench to the main file. So if we give value for clock, for example, we give 0, it will send 0 to this file and run this. Okay, now this is the clock process. We make a clock because we generate an imaginary clock, because we cannot provide a physical clock in our test bench because it is imaginary. So we make a clock and we set a clock period which is 10 nanoseconds. So half a clock period it will be 0, and for half a clock period it will be 1. So 0 1, it will toggle between 0 and 1, and this will be continuous. And now this is our stimuli. Basically we are providing the values. I This is because the values have to be provided in unsigned. So we use, so whenever we are sending a value in VHDL, uh, sending a decimal number, we have to use the command to unsigned, then a bracket, and we write the value in decimal, comma, the number of bits it is. So to 20,016 bits. If we want to send the value in hex, we just write x and then place two semicolons and place our value in the number of bits we need to be. So it needs to be in uh, 4 hex. So this would be what, 4 bytes. So we could either we could so 64 is 100. We can change this and write to unsigned 116. This would be the same as uh, you know writing x 0016, sorry, 0064. So this is the same as writing that. So these are different methods to approach uh, or to write decimal numbers or hex in whichever format. You can also write in binary. Okay, so these are the inputs that we want to send. Okay, if you want to change it, we can send it, for example, 49 as well, and we will get quotient and uh, remainder for that particular input. Okay, and this waits for 200 nanoseconds. So this, after sending these inputs, it will wait for 20 nanoseconds, and after this it will end this particular process. Okay, so uh, this concludes our non-restoring algorithm quartus implementation. Thank you.